Hello students, hope all of you are fine and doing well. Now in this video, let's go ahead with the topics that we have been discussing about simple harmonic motion. We have discussed about the basic definition of simple harmonic motion in the previous video. So here would be looking at the application of it, that is simple pendulum and spring mass system. So first let's look at a simple pendulum. What is a simple pendulum? A mass tied to a string of length L and hanged somewhere. We slightly disturb the simple pendulum. You can see that we are disturbing the simple pendulum slightly from its mean position and then leaving it. Now let's see what is the restoring force acting on it. So if you see, mg would be acting in this direction and tension would be acting upwards. If I take this is theta, then this would be mg cos theta, which would be balancing the tension, and mg sin theta is the force which is trying to bring it back to the mean position. So the restoring force that is acting on it is minus mg sin theta, minus because it is trying to bring it back to the mean position. Now let's say if theta is very small, so I'll say for small values of theta, for theta tends to 0, I can write sin theta, I'll just take this as x. If I for small values of theta, I can assume this to be a straight line x, and this is L, and this is 90 degrees. So sin theta is equal to, I can write it as x by L. So that would imply F equal to minus mg into x by L. So if I compare it with the expression F equal to minus kx, I'll have k equal to mg by L. Now the expression for time period is given by t equal to 2 pi root m by k. So let's substitute the value of k here. Then I'll get t equal to 2 pi root m by k is mg by L. So mm cancels. So from this I get t equal to 2 pi root L by g. This is expression for time period of SHM when a simple pendulum is slightly disturbed from its mean position. Again, a very important thing, if the angular displacement, that is if I pull it to further height and leave it, then I cannot use this expression. And if I cannot use this expression, then the motion is not simple harmonic and this equation would not be valid. So this equation is strictly valid for very small amplitudes. So I again say it is theta tends to 0. Only in that case oscillation is simple harmonic. And otherwise there is an oscillation, but that oscillation is not simple harmonic motion. So t equal to 2 pi root L by g. Now let's look at the parameters on which the time period of simple harmonic motion depends on. It depends on the length. Now what is the length? Length is the distance or separation between the point where it is hanged, between, I'll say, the point of suspension where it is hanged to the center of mass of bob. So it is, so this is what is length, exactly center of mass of the bob. If I'm taking a solid bob, the center of mass would be exactly center. This would be the effective length. Now why I'm very specific about this length is there are questions where the bobs are given of situations where the bob center of mass is changing. For example, I have a hollow sphere acting as a bob and it is filled with water. Then where is the center of mass? At the center. Now if I keep a small hole at the bottom of it, what will happen? The water level keeps on decreasing. When the water level keeps on decreasing, the center of mass keeps on going to the lower end and the effective length would increase. So in that case what will happen? Although the time period does not depend on the mass of the bob, because of the change in position of center of mass, there would be a change in time period. And finally, once again, when the bob is totally empty, the center of mass shifts back to its original position. So here the time period will slowly increase and then again come back to its original position. So that is why the length is again the separation between the point of suspension to the center of mass of the bob. So this is one thing. And the other thing is, when we are considering about forces, we are considering the forces are restoring force. Only force that is responsible for oscillation is restoring force. Other forces are not responsible for oscillation. In this case, you can see tension is acting, mg cos theta are acting. They are not contributing to bringing the bob back to its mean position. So they are not restoring force. So we don't consider that. So if I have any other force acting along the string, I can have another force, like I keep a charge plus q here and another charge q here. There is an electrostatic force which is acting between these two lengths, which is affecting the bob. This force will not affect the time period of SHM. The reason for that is this force is not this force or a component of this force is not contributing to the restoring force. That's why it will not affect the SHM. So I can say that any force acting along the string of a simple pendulum would not affect the time period of simple pendulum. So that's what we have seen. So the other things that we have to see is, so t equal to, we have 2 pi root L by G. Other questions that we have is, I can write t square is proportional to L if we take G as constant. Now there are other questions where we take a simple pendulum from Earth to some other planet, then there is a change in gravity. So if there is a change in gravity, then you can find what is the time period of SGM. Other situations that we have is, I keep this bob inside. Let's say I put this bob inside a fluid of density, I'll say rho f, and the density of bob is rho b. In that case, what will be the time period? You can find the effective, this would be the effective force. Effective force would be how much? You can write the effective force is mg minus upthrust into sine theta. So everything else will be same. The effective force would be mg minus upthrust. Now other situations that we have is, I have a simple pendulum which is hanged in a vehicle which is moving with an acceleration a. Now if this simple pendulum is hanged in a vehicle which is moving with acceleration a, then what will happen? The equilibrium position will be shifted. Now if I disturb this pendulum will only oscillate in this part. Now in that case, what is the net force acting in this direction? Net force would be equal to m into under root of a square plus g square. Why under root of a square plus g square? Because mg is acting like this, ma is acting like this. This is the net force. So what will be the time period? Time period would be 2 pi root L by the effective acceleration, that is under root of a square plus g square. So this is when acceleration is horizontal. Now if this pendulum is in a lift and the lift is moving up with an acceleration a, then the effective force here is m into g plus a. In that case, time period would be 2 pi root L by g plus a. Similarly, if lift is moving down with acceleration a, time period would be 2 pi root L by g minus a. In this way, we can find time period of simple pendulum depending on various motions associated with simple pendulum. Now let's look at another example of SHM, that is spring mass system. Now we know that when a spring is compressed or extended, so when it is extended, a restoring force acts towards the mean position. Similarly, when it is compressed, a restoring force acts towards the mean position. So we have this restoring force given by F equal to minus kx, right? So because F equal to minus kx, from the same expression we have T equal to 2 pi root m by k. So this is time period of spring mass system, where m is the mass which is attached to the spring and k is the spring constant of the spring mass system. Now you can see that unless what all factors does the time period depends on? Time period is directly proportional to square root of mass, and time period is inversely proportional to the spring constant and nothing else. These are the only things on which the time period of a spring mass system depends on. Now let's look at various combinations of the spring. Now here I have K1, K2. This is series combination. If K is the effective spring constant, in series what do we have? In series we have 1 by K equal to 1 by K1 plus 1 by K2. So I can write 1 by K equal to K1 plus K2 by K. K1, K2, right? Or K would be equal to K1, K2 by K1 plus K2. This is what is time. Effective spring constant. So the time period in case of series combination would be 2 pi root m by, we can write K1 K2 by K1 plus K2. This is what is the time period. Similarly, in parallel combination K1, K2 in parallel, we know that effective spring constant is, we have K equal to K1 plus K2. So then it is pretty simple, T equal to 2 pi root m by, I can directly write effective spring constant K1 plus K2. So if we have combinations of spring, then the time period would be equal to 2 pi root m by the effective spring constant of the combination. So in this way we can find time period of a spring mass system. So let's have a quick review of what all things we have done. We have seen what is a simple pendulum, then we have derived an expression for time period of simple pendulum which is equal to 2 pi root L by G. And we have seen that what is length of the simple pendulum. Length of the simple pendulum is the distance between the point of suspension to the center of mass of the bob. And that's why if the position of center of mass of the bob changes, then the time period changes. So time period of simple pendulum does not depend on the mass of the bob. And then we derived an expression for spring mass system, and then we saw how we find the time period when the spring when we have combination of springs instead of a single spring. So this is what is there in applications of simple harmonic motion. The examples that we have taken is, one is a simple pendulum and other is spring mass system. Hope you could follow this. Thank you very much for watching this video, and also thanks a lot for watching all other videos of Get My Classes. And if you have not watched it, you can look at the other videos of concepts as well as solution to questions of different levels. Thank you very much once again.